Alright, this lecture is intended to be a review of rotational kinematics and how it relates to translational motion, which is what we were studying for most of the year. So here I have a circle, and at some distance away from the center of the circle, and in this case I'll just make it the full radial distance away, we have a point, which is denoted by that red dot there. And this red dot is going to go from one place to another place because the wheel is spinning. And so I can just describe the spinning of the wheel as being something like this. So it's rotating clockwise. What we would hopefully describe it as is going into the screen as the direction of the rotational motion. In any case, so the point here goes to there, and then it goes to there, and so on. So it just follows along through the circle. And I could describe my displacement x, or delta x, I'll use delta x to be a little bit more formal, to be the change in position. And the whole problem with this is with rotational motion, if I choose a different r, maybe my r is much smaller, my x's are much different. My changes in position are much different. The nice thing that we can do is that no matter which r we choose, whether the r is this little bit right here, or whether it's the whole radius of the circle, a point at the edge of the circle, or a point towards the middle, the change in rotational position is constant. Okay, so it's the same, that's the same angle there as it is out here, as it is in here. So we have the same angle, or the same angular change no matter what. So this is how we describe the angular change in position, and that's in radians, which, as I described earlier in class, isn't really a unit. It's just kind of a placeholder unit, because to get angle you just do the you do s over r, where s is the arc length. So that would be the length of this arc here divided by the radius will give us the angle. If I was measuring these in meters, I would get meters over meters, which would give me nothing, no units. But to differentiate between the no units that we get when we calculate the angle and other no units, we call them radians, because they do represent angle. At least then we know what we're talking about. Okay, so let's look at some of the other things. We'll breeze right through them. Because we have an angle and we have the motion of a particle, let's say, so this takes a certain time, and I'll call that time t. So this change in position takes a certain amount of time. That means the change in the angle takes a certain amount of time as well, and we'll go ahead and we'll call that omega. So omega is equal to the change in the angular position divided by time, just as the change in linear position is equal to the, or divided by time is equal to the linear velocity. So I have angular velocity, or omega, is equal to delta theta over t, and that's in radians per second. And as I said before, it is into the screen in this case. Now we also have some translational terms, and this means tangential acceleration, and this is what we've been dealing with for most of the year. The change in straight line motion is really what we're interested in, and it has to do with speed. So if we notice a speed change, we have tangential acceleration. So far in this example, there is no speed change. It looks like it's maintaining a pretty much constant speed. Now I can go ahead and change that. So in these next angles, you can see that there's a decrease in the angle. So the first two, we had a nice constant angular velocity. We had a nice constant change in the angle. But in these future ones, the ones going forward, we see that the angle is getting smaller and smaller and smaller. Okay, so we start off with bigger angles, gets a little smaller, a little smaller, a little bit smaller. So in this case, we now have a change in the angular velocity, a change in the rate of the motion, and so that gives rise to an angular acceleration. Okay. In addition to the angular acceleration, the point at the edge of the circle, or anywhere really in the circle, but we'll focus on the one at the edge here, is covering less and less distance as time goes by. So this is equivalent to an object slowing down. So we definitely have this in play. There is another type of linear acceleration, which is always present when you have things going in circles, and that's the centripetal acceleration. Sometimes it's called radial acceleration. Okay, and the vector for it arises from the radius, so it's along the direction of the radius is how it works out. And so it's always going to be into the circle. For us, it's actually in opposition, so we'd have to, if we were being technically correct about it, we'd throw in a negative sign here, but we're not going to do that. We know that the centripetal acceleration is into the center of the circle, and that's going to be the case regardless of whether there's a change in velocity or not. So you can see that we have, this doesn't care about the velocity changes that's occurring, it just cares, is there a velocity, what is the velocity right now? So the centripetal acceleration will be less as we go to slower and slower velocities as we're moving less and less quickly, but it will still be there so long as it's going in a circular type of a pattern. Now one of the important things is how do we convert between all of these different things? And it has to do with the radius. Obviously, the further out we are from the center of the circle, the greater the change in position is going to be. And if we have a greater change in position, that's going to lead to a greater velocity. And when the velocity changes, is going to be a greater change in velocity the further out we go, or a greater acceleration. This also cares about how far away you are, but we're going to focus on these ones primarily. How do we relate these ones to the rotational equivalence? And it does just have to do with the radius. So if I want to find out what is delta x, I would just set it equal to delta theta times r. Now, technically, what we have going on here is a cross product, which I described a little bit more formally previously, but it's the cross product between the change in the angle and r. The same would be true for omega and v. So if I have something that's changing its position at a certain rate, we can find the linear velocity by knowing what the angular velocity is and the radial distance away. So to give you a quick example before we go to a slightly more complicated one, let's say that we have an angular velocity of 10 radians per second, and I have two possible radiuses away. Maybe one is half of a meter away and the other one is 1 meter away from the center, so at the halfway point and fully at the edge. Well, there's no difference in the angular velocity because it's traveling through the same angle no matter where it's located from the radius. But in terms of how fast the point itself is moving, if I'm just looking at a particular point, how fast is that point moving? Well, that's going to depend on the radius. So the velocity at the halfway point out, so right around here, let's say, would just be 10 times 1/2, or 5 meters per second. The radians go away because they're not a real unit. The velocity at the very edge would be 10 meters per second. Alright, and since this one has gotten to be a little bit long, but hopefully it clarifies the relationship between the various components, what I'm going to do is just a quick example in another video, kind of relating all of this together in a little bit more detail, a little bit more complexity, and really talking about rotational kinematics with frequency and period and that type of a thing.